My name is Hunter Blanton. I will be presenting our work titled A Structure-Aware Method for Direct Pose Estimation. The goal of this work is to perform single image localization. In this task, given a query image, we want to determine the position and orientation of the camera with respect to a known map of the area. The traditional approach for determining the camera pose from a single image involves computing 2D, 3D correspondences. That is to say, for some set of pixels in the image, we determine the corresponding 3D location in space that is captured by the pixel. Once these correspondences are established, a perspective endpoint algorithm is used to determine the camera pose that can observe the given points from the given pixels. The difficulty in this approach comes from how to generate a large set of accurate correspondences. A popular alternative to correspondence-based approaches is using a CNN to directly learn the mapping from image to pose. Instead of computing feature correspondences, information about the scene is baked into the weights of the network so that the pose of the image can be directly regressed as the output of the CNN. Since this does not depend on feature matching, it is much simpler and can be applied regardless of scene complexity, but often performs far worse than traditional methods. Inspired by recent work in computer vision for dense geometric prediction, we wish to improve the accuracy of CNN-based pose regression methods by incorporating geometry directly into the network. The idea is to use both scene coordinates and depth estimates to perform pose estimation. Image depth is the distance of each pixel to the center of the camera and is defined purely by the relative position of the captured surface to the camera. On the other hand, scene coordinates are the absolute coordinates of each pixel in 3D space and are defined with respect to the global reference frame. The transformation between the camera frame and the global frame is exactly the camera pose. The important thing to note is that the depth and scene coordinate images represent exact correspondences at each pixel. So if we can accurately predict these two quantities, then the camera pose can be easily computed using a closed-form, differentiable solution to the rigid alignment between the set of points. Here we present an overview of our novel end-to-end approach to single image pose estimation. We first predict scene coordinate and monocular depth to obtain corresponding point clouds in both the global and local coordinate frame. Then we use the COPS method to perform differentiable rigid alignment of the estimated point clouds. We use a correspondence weighting CNN to allow for outlier scoring before the alignment step. All of these steps are differentiable network layers, allowing us to optimize the full network in an end-to-end manner. Unlike typical absolute pose regression methods such as PoseNet that use generic CNN architectures and attempt to implicitly memorize the scene, this architecture decomposes the task into explicit subtasks that are designed specifically for pose estimation. We compare our method to several other CNN-based methods for pose regression. We report median error of each scene of the Microsoft 7 scenes dataset in meters and degrees. Our method significantly outperforms all other methods in terms of orientation error. Our method also performs best in position error in all but 2 cases. We report the average error on all scenes, which shows the significant decrease in error achieved by our structure-aware pose regression approach. Note the highlighted rows in the table also use scene coordinate regression for pose estimation. These methods perform much worse than our method, which shows that the use of geometry prediction alone does not improve pose regression accuracy. We show the intermediate outputs of the depth, scene coordinate, and weighting networks. One thing to note is that we do not mask out invalid data in the loss function. Rather, we allow the network to fully memorize the regions of the scene where there is no training data. We observe that this improves pose accuracy in the final network. Also, we show that the weights generated by the weighting network are capable of correctly segmenting regions with incorrect predictions. We show this by visualizing the endpoint errors computed by using the estimated depth, scene coordinates, and final pose. In these images, dark and light regions correspond to low and high values respectively. We see that the endpoint error is typically high in regions with low correspondence weight. In summary, we propose a novel structure-aware method for pose regression using a CNN. Our method makes use of depth and scene coordinate prediction to frame camera pose estimation as a rigid alignment problem. We show that our method outperforms other CNN-based pose regression approaches. Please visit our poster session for more information.